Right, please confirm if you can see the slides on the screen. Boleh nak minta saya jadi reference? Yeah, boleh, of course. Yeah, no problem. Some companies will really call. So I got called a couple of times by companies due to this reference thing. Okay. Bekas pelajar yang nak kerja after intern, applying to new companies. Before 20 months sharing weeks. Okay, yeah, you can put my name on, but tell me first, so supaya saya aware. Nanti kalau company call, then I say, oh, saya tak tahu pun, then bad impression on you. Okay, yep, alright. Make sure you beritahu saya supaya saya aware. Don't just put it supaya saya tahu siapa yang apply. Nanti saya tak ingat kan, so susah. Cakap, oh, I don't know this student. Habis, you tak dapat if you application. Then you cannot blame me, okay? It's not my fault. Tell me first. Okay, let's continue. Thermal oxidation. So I've provided the asynchronous recording on the Tuesday's class to introduce thermal oxidation process. Right, thermal oxidation is the very first process that we want to do on our bare wafers. So remember, we've discussed the conversion of sand to polycrystalline silicon, and then conversion of polycrystalline silicon to monocrystalline silicon ingots, and then we cut the ingots into wafers, and then we go through wafer preparation steps, and then we go through wafer characterization steps. We've discussed a clean room and what it takes to be a clean room, what are the do's and the don'ts in the clean rooms, contamination sources and all those stuff. And now the wafers are ready for the fabrication processes. Okay. So I want to go through this. I've explained a little bit, so I'm just going to go through briefly again. We have discussed about MOSFET in our previous course, ZAT487, quite extensively on the last part of the course. And by now you already know that the structure of a MOSFET consists of a gate, right? A gate on top, and you have a very thin layer of gate oxide under the gate. Okay, about the gate oxide still, and then of course you have the wafers. Your wafer as the body can be p-type or n-type, and then you form the source and the drain on the left hand side and on the right hand side of the gate and gate oxide, right? So these can form either p channel or n channel depending on whether your MOSFET is p-type or n-type, and that p or n-type depends on the channel, right? Not on the wafers, but on the channel. So in this case, we're talking about n-channel MOSFET because your source and the drain are both of n types, right? So we've also discussed about the properties of the thermal oxide to form the gate ox, right? We also discussed the properties of the oxide in order to form field ox. Okay, gate oxide is under the gate, but field oxide is between adjacent devices from your first chip to the second chip. Sebelah-sebelah, you akan nampak dia punya isolation because you need to isolate one chip from another by the field ox. Okay, so we have discussed on a couple properties. For example, it has to be the thermal oxide has to be an excellent electrical insulator. It needs to have a high breakdown electric field, or else if you don't have this, then if you apply a high VG, for example, then it's just gonna break down. Or even though, for example, if you don't apply a high VG just yet, it may already break down if the quality of the oxide is not good, right? So when we talk about thermal oxide, so we are talking about growing oxide, okay? Thermal oxide ini maksudnya kita grow oxide, kita tumbuhkan dia. So has anyone worked on any silicon dioxide deposition during your FYP? Has anyone worked on sputtering of SL2 or some other methods to deposit SL2? Anyone? Sputtering ke, CVD ke? No? No? Tak ada. So, tak ada right. So, you can, bila you ada wafer, for example, you ada wafer, silicon wafer, you can have silicon dioxide on the wafer by many approaches. Okay. So one method that we're discussing here is called thermal oxide. Thermal oxide means we grow the silicon dioxide on the silicon wafer while consuming the wafer. Sambil kita tumbuhkan dia, sambil kita grow tu, kita akan guna silicon yang ada tu. So dia akan makan silicon lah basically. We're gonna look into that today. And how is the mechanism around this. So dia akan gunakan sebahagian daripada silicon, dia akan consume sebahagian daripada silicon to form the silicon dioxide. On the other hand, you can also have silicon dioxide deposited. So the term is deposited, different. So kalau thermal oxide ni kita grow, kita tumbuhkan dia, we grow the oxide. Satu lagi kita deposit the oxide. Deposit ni kita letak oxide, kita tumbuhkan juga, but then we deposit the oxide on the silicon wafer without consuming any silicon. Dia macam duduk macam kita kot je. Tapi kalau you grow oxide, you tumbuhkan oxide daripada silicon tu sendiri, right? Silicon tu is the supplier of the silicon dioxide. Okay, but if you deposit, dia macam cat je, you cat, tapi dia tak kacau apa-apa pun, the underlying surface. The underlying surface is exactly the same. So that's different between thermal oxide that we grow and silicon dioxide that we deposit, right? Two different terms, grow and deposit. Okay, so it has to become thermal, and then silicon dioxide has to be, if you want to use this silicon dioxide as a mask, boleh pakai dia sebagai mask. So we're going to see later on where you can use this as a mask. So that means you use silicon dioxide to close certain regions on the silicon so that you can perform diffusion process. Diffusion too means a process that we incorporate dopants into the silicon, okay, to make it more p-type, more n-type, or more p+, or more n+, or p++, n++, in certain selected regions. Kalau kita nak pakai, kalau you nak dope the whole silicon, blanket means semua. The word is usually blanket kalau kita pakai dalam industry. The whole surface, then you don't have to close certain areas and open certain areas, right? Because you want to go for blanket diffusion anyway. But in the fabrication of devices, typically you want to use certain regions to be doped and certain regions not to be doped. So in this case, you need to use mask. You can tutup certain areas and leave it open at certain areas. So in this case, you can use silicon dioxide as a mask, but the silicon dioxide has to have a minimum thickness. Okay, we're going to cover that later on as well. If you prepare your oxide with thickness less than the minimum thickness, it's not going to block the diffusion of phosphorus or boron or some other gases. Dia tak akan boleh block, so you're going to get the doping still under the region. Okay, we're going to look into that as well. So selectivity has to be very high between silicon and silicon dioxide so that you can etch later on. So we normally use HF or hydrofluoric acid. Yes, I explained kalau jatuh atas kulit tu, you won't feel a thing yet. It's just gonna penetrate through your skin and eat your bone right away then. Okay, lepas tu barulah you akan rasa sakit. So this acid HF is super dangerous, and it's used in the fab to remove silicon dioxide from the silicon. So you nampak ni, kalau nak remove this silicon dioxide, you just masukkan this silicon dioxide on silicon into a beaker or container containing HF, room temperature, at certain mixture with DI water, deionized water, 18 mega ohm we discussed before, and then dip it for like a few seconds, and then when you uncut, the surface is going to be completely hydrophobic. Hydrophobic. What is hydrophobic? What is hydrophobic that we learned before? in your previous courses kot ataupun kat sekolah ke. What is hydrophobic? Kat sains sekolah menengah belajar kan? Hydrophilic, hydrophobic. Anyone? What is hydrophobic? Come on, someone. Takut air, benci air, right? We used to learn something like suka air or benci air. Okay, tak boleh mix with water, okay? So, what's going to happen if it is, bila you ada silicon dioxide on silicon, kalau you celup dalam DI water, it's just a simple test lah. You ada beaker, ada DI water, deionized water, you ambil silicon dioxide on silicon punya sample, you dip it into the solution, to the water, you angkat, you akan nampak water sticking on the surface. Untuk yang kiri ya, if you have silicon dioxide on, kenapa tak boleh ni je? Number one, you're gonna get water spread across the surface. Ataupun dia ada air dah lekat. So that's a sign of silicon dioxide still present on the silicon. So lepas you HF dip dekat tengah ni, so you go to state number 2, condition number 2, to know that your silicon dioxide is completely gone, okay, from the surface. You boleh test sekali lagi selepas you HF dip, test sekali lagi kat DI water, so it's gonna be hydrophobic. Maknanya dia akan benci air lah. Maksudnya kalau you tengok dekat apa you celup, angkat, akan nampak certain spot je ada air ataupun completely tak ada langsung. Okay, so that means the surface is now hydrophobic. Air dah tak lekat dah. So we call that hydrophobic. Suka air, benci air. In this case it's tak suka air. So silicon dioxide is an amorphous material, so that means it doesn't have any periodic arrangement of atoms like what we learned in 386. Okay, monocrystalline, polycrystalline, but silicon dioxide in this case is an amorphous material, so there's no periodic arrangement at all. You just find atoms everywhere in no arrangement whatsoever. Right. So when you talk about thermal oxidation process, there are two ways to do it. Okay, there are two ways. The first one is called wet oxidation. Okay, first one is called wet oxidation, where you use water vapor to introduce the oxide component. So water vapor will be your oxidant material. We call that as oxidant material. Material yang kita supply in order to proceed with the growth process, with the oxidation process. So you can have a look at the equation. Use silicon wafer plus H2O in the form of vapor, and then you're going to get silicon dioxide on the silicon plus 2H2. So bila you grow this thermal oxide near your silicon, if you put this silicon into the furnace, you can watch a video saya dah letakkan pasal oxidation furnace. We have a look at that. The very slow process, loading and unloading stuff. Bila you dah grow, you're gonna get oxide like this. Bila you masuk dalam furnace, dia akan cover oxide keliling keliling wafer, because you have silicon everywhere, right? Silicon on the top, silicon at the bottom, silicon on the side, everywhere silicon. So since silicon is the source of the growth process, so you're gonna have silicon dioxide literally everywhere. Okay, so that's process number 1. Process number 2 is dry oxidation. So you use your silicon wafers, masukkan dia dalam furnace, but then you don't use water vapor anymore, but instead use oxygen gas. So there's no wet component in the process, just gas coming in. So you're still gonna end up with silicon dioxide, sama macam kat atas juga. But there are differences in the properties of the silicon dioxide grown through wet oxidation versus dry oxidation. But you're still gonna get silicon dioxide essentially. It's just that the properties are different. Okay, so let's review the process. So thermal oxidation, heat is added into the oxidation tube. You boleh tengok ni dekat online yang saya dah letak tu dekat e-learn tu. Tengok how does the tube looks like. Okay, so you're gonna have quartz tube, horizontal in this case, and then these are all wafers loaded on quartz boats. Okay, quartz boat ni kita panggil boat lah. Boat ni macam boat lah, nak bawa passengers kan. Tapi in this case the passengers are wafers. So quartz boat kita letakkan vertical, and then if you're using dry ox, okay, dry ox means dry oxidation. So I can just mention ox. The dry ox in this case, just use oxygen, let it in, and start oxidation process at whatever temperature. So in this case, typically 900 to 1200 degrees C. And if you increase the temperature, the rate of oxidation increases accordingly, right? And the typical range of the oxide grown is within this region, so 60 to 10,000 angstrom, or if you convert that into nanometer, then 1 nano equals to 10 angstrom. So that's 6 to what, 10,000? 6 to 10,000 nanometers. Okay. Dalam fab, the unit that we usually use is either a nano or angstrom. Okay. Kalau you work in a fab yang fabricate low technology node, then probably you'll be using a couple of microns as your dimension. Tapi kalau you work in like Silterra, hardly micron, it's usually in the nanometer region, or sometimes mentioned as angstrom as well. Okay. So you can see the loading and unloading process on the video on Elan. So dry nitrogen is introduced in this chamber as far as process sequence is concerned. So before you start the oxidation process, you have to flow the nitrogen first into the chamber, supaya the oxidation process won't start yet. Okay, so that's why you have to introduce this nitrogen into the chamber to prevent oxidation from occurring. Katalah you tak include nitrogen dalam chamber, and then you increase the temperature to say 1000 degrees C. There's no nitrogen coming into the quartz tube. There's no oxygen coming into quartz tube. Will you get any thermal oxidation on the wafers? Any guess? So there's no nitrogen coming in. There's no dry oxygen coming in. There's no water vapor coming in. Silicons are already inside. Silicon wafers are already inside. Temperature is already set at 1000 degrees C. Will you get any thermal oxidation on the silicon? Anyone? Tak ada gas masuk, tak ada vapor. Ada tak thermal oxidation taking place? Okay, I'm gonna say no. Any other? No. Okay. Okay, lagi. Anyone says yes? We have two no's. Any yeses? Akila, how about you? Akila? Yes or no? Well, let's discuss. Akila, no. Arisha? No. Alia? So let's have two more. Semua no ni. Alia and no juga. Siapa lagi? Go. Go dah cakap tadi kan. Hadi? Yes or no, Hadi? What do you think? No. Okay, so it's all no's, huh? Okay. My question is, kalau you tak masukkan nitrogen, kalau you tak masukkan dry oxygen, what do you have in the quartz tube? What gas do you have in the quartz tube? Remember, it's not in vacuum condition. Anyone? Kalau you tak masukkan nitrogen, you tak masukkan dry oxygen, well, there's no CO2. Kita tak masukkan apa-apa gas pun. There's no nitrogen coming in, there's no water vapor coming in, there's no dry oxygen coming in. Yang ada dalam chamber now ialah ambient oxygen. So ambient kan oxygen. If it's not in vacuum, then we have air, right? Ambient lah, ambient daripada kita tak induce oxygen masuk. But then there will always be some level of oxygen, right? So the ambient yang memang dah ada kat situ, because it's not in vacuum to begin with. Unless dalam vacuum condition, then obviously you have evacuated The oxygen, yes, persekitaran punya ni. So you introduce a dry oxygen to increase the oxidation rate. So that doesn't mean you don't have oxygen in the chamber to begin with. So oxygen, bila you run apa ni, bila you you load the silicon wafers, you set the temperature at 1000 degrees C, even though you don't have any water vapor coming in, there's no nitrogen coming in, no oxygen coming in, you will still have an appreciable rate of growth yang you cannot control sebab you don't measure the ambient exactly. So maksudnya you still get some level of oxygen yang akan ada sebab dia ambient persekitaran punya. So kalau you tak buat apa-apa, when actually for your information, if you don't do any thermal oxidation process yang kita discuss sekarang, kalau you ambil silicon wafer, you letak atas bench, letak atas dalam masuk no lab, letak atas bench, expose to ambient, you tak buat apa-apa pun, room temperature, then you leave it for like a couple of hours ataupun say 1 day, 2 days, you come back after 2 days, you measure oxygen, you measure oxide, you will get to see some oxide form, and this is called native oxide. Okay, ini important info. Native oxide ni you don't grow, but then it's naturally there. Native oxide. Okay, native oxide. So no oxide yang formed by ambient process. You tinggal je, you measure. After 2 days, you will see some thickness of oxygen. And we call that as native oxide. And the typical native oxide is around 3 to 5 nano. Okay, depending on the temperature, humidity, the duration that you left the silicon wafers on the bench exposed, typically in the region of 3 nanometer to 5 nanometer. So if your oxide that you want to grow is say in the region of 100 nanometer or 200, this native oxide mungkin tak akan affect that significantly, right? But if you want to grow your oxide as the gate ox in the region of 4 nanometer, 5 nanometer, 10 nanometer, then this 3 to 5 nanometer of native oxide is already like 30-40% of the total oxide, isn't it? And at this point, it's going to be significant. So that's why you need to do the HF deep blue. Then deep blue, remove the oxide, make it completely hydrophobic, then load the wafers into the oxidation chamber, purge, we call that purge, ataupun flow lah. Some condition we call that purge, ataupun flow, the nitrogen into the chamber to make sure that there is no oxidation occurring at all, okay, before you start your intended oxidation process. Let me just continue for a few minutes, then we take a break for 10 minutes. Okay, then right, so that's the first point. Then nitrogen gas flow shut off, then stop the nitrogen flow, then oxygen coming into the chamber in the form of water vapor or dry oxygen added to the chamber when the temperature has reached the intended temperature. Bila masuk tu, that means you start the oxidation process there and then, right? So it can be dry process, it can also be wet process. Then lepas you dah grow your intended thickness, say 10 nanometer, for example, of thermal oxide, then nitrogen gas is reintroduced. You stop oxygen, you on balik nitrogen, masuk dalam chamber, then it's filled with nitrogen. That will stop your oxidation process from continuing from the previous previous step lah. So that's why dalam fab ataupun you go for some other factory, kita akan panggil recipe. So for every process that you are going to run, we call, there's always a recipe that you have to load. Macam recipe masak, exactly that. And this recipe is outlined in the specs. Remember the process specs and everything? So every process that you run on any equipment in the fab requires a recipe. Macam recipe masak, exactly. So that means in this case, you load nitrogen for how long? What is the flow rate? What are the conditions of nitrogen? And then nitrogen stop after how long? Then oxygen coming in. At what rate? Water vapor or dry? For how long? At what temperature? For how long? Then lepas you stop, you can remove the oxygen. Then you set the nitrogen to come in at certain flow rate for how long. Semua ni akan spell out. So first step is nitrogen, Second step, oxygen coming in, then nitrogen coming in. The process, you cool down the temperature, then only you unload. Okay, before this, maybe you ram the temperature, then you load the silicon wafers. So there'll be like, say, I don't know exactly, perhaps 10 steps. So these 10 steps are outlined clearly in the process recipe of this particular process to grow 10 nanometer of dry ox, for example. Okay, so semua dah ada recipe ya. Recipe ini proses engineer yang akan create, okay, and validate and test run before you get to run your mass production. If you want to introduce a new recipe or change the recipe, you have to go to the review board. Okay, we normally call it as QRB, quality review board, where you need to present your recipe and then the quality of the recipe of the oxide in the test run on test wafers, bukan mass production lagi ya. You can run, say, 10,000, a couple of thousand test wafers to prove that the process is working, get approval in the quality review board, approve, top management akan approve, barulah you can turn on the recipe to mass production. Selagi tak dapat approval, you will not be able to run your new recipe or improved recipe in the mass production. Okay, so that's how it goes. So that's more on the operational side of the of the job as a PE while doing this process. So saya akan slate from time to time so that you understand how does the whole thing works in it on its own, right? So if you talk about dry oxidation, then the oxidant, and remember oxidant is the word, is dry oxygen, the precursor material. So the typical thickness of dry oxidation is less than 1000 angstrom. So 100 nanometer and below, you normally use dry ox. If you go for above 100 nanometer, you go for wet ox. Okay, so it's a very slow process for dry ox. So the growth rate is like 14 to 25 nanometer per hour. So dalam sejam hanya dapat about 20 nanometer saja sejam growth process. So it's a very slow process. So thin oxide growth less than 15. For feature size less than 1 micron. This is not the rule of thumb, tapi generally this is how it goes. So it really depends on what you want to grow later on as your device. So you can include additional species to the growth like ACL, TCE, TCA. They will help to decrease the pressure and which will slow down the growth rate. So we're going to see later on the relationship between pressure and growth rate into this topic. Okay. So wet ox, on the other hand, we use water vapor as the oxidant. So it's a faster growth rate, say 100 to 120 per hour. So relative to 14 to 25 now for dry ox. So wet is faster, so they are the water vapor. You can also have a look at the video I shared on Elon. They compare wet and dry side by side in terms of the growth rate, right? So this is usually a preferred oxidation process for thick oxides. So thick here, if you're talking about 100 nanometer and above, then you might want to go for a thick oxide. Okay. So function of oxidation, let me just finish the first part that I covered in the asynchronous class. You can use your oxide for passivation. We discussed this in 386 as well. You can use it for surface passivation. We talked about dangling bonds last time due to termination of lattice. Remember, kita potong silicon kan. So in this case, if you relate to the previous process, kita dah grow ingot monocrystal, and then you slice the ingot into wafers using wire sawing or diamond blade or something. Then you terminate the lattice, right? You literally terminating the lattice, you potong. So dia akan dapat damage on the surface, even though you have done the lapping process to smoothen the surface and to do CMP to make sure that you have a smooth surface, but there are still electronic defects, okay? Electronic defect. So this is your wafer. So you nampak macam smooth lah, but then electronically you cannot see. If you look at the band gap, for example, this is like EV, EC. We talked about this in 386. EG is a band gap. So you're gonna have some trap states. So electronically active due to dangling bonds that need to be passivated. Kalau you tak passivate these dangling bonds, then they are going to affect the electronic performance of your device eventually. Electronic performance. So that's why you have to do this passivation process by using silicon dioxide on the surface. It will help, right? So how do you check? Any idea how do you check whether the surface is well passivated or not well passivated? Any ideas? So you have got the wafer, then you've done the passivation using silicon dioxide. Macam mana you nak cakap kata, okay, now the surface is already well passivated and ready for the next processes. How do you tell? How do you check? Any specific parameter you can check in order to prove that? Ataupun you buat passivation tu tak jadi pun, or it's not working. Any ideas? Anyone? Any guess? Kita belajar dekat passivation juga dalam 386 last time. Satu parameter tu. Remember this one? Apa ni? What is this? What is this? What is this parameter? Anyone? Kavina? What is this? Mac, what is that parameter? Belajar tu kan, 386. What is this? Anyone? Apa parameter ni? What do we say? How do we pronounce that? Talk ke? Are you sure talk? Talk macam force ya? Anyone? Tau kan? Tau. Tau, right? So, what is tau? Carrier lifetime. You can check, you can measure carrier lifetime. Tahu dah, ha? Dah tahu sekarang. So, carrier lifetime, you can check the carrier lifetime of the wafer after passivation versus before passivation. Okay, carrier lifetime. So, tau ni akan affect what's next? L, right? L d tau square root. Diffusion length equals to diffusivity times carrier lifetime. Kita belajar dekat passivation juga. Pada 386. Okay. L equals to square root of d tau. Right? Sekarang dah tahu, eh? So you can check that to prove that your passivation works. Right? So masking, as I explained tadi, you want to block certain areas from being doped. So in this case, you can only dope this region, but not here and not here. If, only if, your thickness of your oxide is above the minimum thickness. Kalau dia below minimum thickness, then it's just gonna dope anyway. Macam tak ada oxide pun kat situ. So it has to exceed minimum thickness. T-ox exceed T-ox minimum. You can say something like this. Okay. Kalau okay, barulah is gonna block. Else is not gonna block. Right? Okay, so let's have a break for, now it's almost 11. Let's have a break for 10 minutes. Okay. Then we're gonna come back at 11:10 and continue with this masking onwards. Okay. Any questions so far? Ada soalan? Ada apa-apa tak faham? Before we move on. All good. Ada, sekarang dah tahu Mac dah tahu Okay. Soalan Right then, so I'll just stop sharing first and turn on my camera. I'll see you again at 11:10. Right, inshallah. Okay, bye-bye for now. Okay, Assalamualaikum. Let's continue. Sekejap 10 minit ya. Tak sempat apa ni? Apa pun. Duduk dah 10 minit. Okay. Let me share again. Okay, please confirm if you can see the slides on the screen. All right, cool. So, the next function of oxide layers is as masking, as we talked about just now. So, for this function to take place successfully, we need to have a minimum thickness of the silicon dioxide in order to mask against the dopants, phosphorus, boron, or some of the dopants. So maksudnya kalau the minimum thickness is not met, then it's not going to be able to block the dopant successfully on the selected regions. Okay. So for example, so let's check it out on this graph. If say we want to use the silicon dioxide to block boron, okay. Katakanlah you had a silicon wafer N-type. Oh, sorry. So we are now using N-type silicon 100. Then you want to diffuse a very thin layer. Sorry, this is your oxide on the left and on the right. So you want to block the dopants on the left and on the right, but you want to diffuse this central part with boron to make it p-type, so that you have a p-n junction, right? So you want to make this p-type, the central part. So let's understand the graph. You want to dope boron in the central part, and you're running the process at 1100 degrees C. You're running the diffusion process 1100 degrees C for say 2 hours or 2 hours. So what is the minimum thickness of silicon dioxide needed in order to successfully block the boron on the left and on the right hand side? Is someone? So we're going to run the process at 1100 degrees C for 2 hours. Diffusion time is 2 hours. So what is the minimum thickness of silicon dioxide needed in order to successfully block? 001. Okay, 1100 degrees C, yeah? Is it? Not 1000 degree, yeah? 1100 degrees C. Okay, I'm going to say 003. Okay, let's see. Ada lagi jawapan lain? 001, 003, 001, too low, Zix, you are referring to 1000, I guess. Any other? 2 hours kat mana? 2 hours. Ini kan? It's log scale, right? So put that to lebih kurang, tak baris eh. So 1100. So that means, yeah, somebody's joining. Okay, so take that to the y-axis, 1100 degrees C. Oops. Yep, so how much? 0.03, right? 0.03 micron. Okay, 003 micron. So 003 micron means, apa nano? You convert that into nanometer. So how much is that, Amiro? 30 nanometer, right? So you need to have 30 nanometer at least. Beyond 30 nanometer lah. To be safe, maybe a couple of nanometer extra. So you need to have at least 30 nanometer of silicon dioxide in order to successfully block the boron from doping the left hand side and the right hand side of the silicon while running diffusion process at 1100 degrees C for 2 hours. Okay, see the description is very, very specific. It really depends on the diffusion temperature, how long do you run that, what sort of dopants are you incorporating, then you have to come back to this curve and see what is the minimum thickness required. Okay, so boleh faham kan? It's clear cut, right? So not that difficult. Okay, the next function is as insulating material, which is as the gate ox in this case, gate ox and GO tulis. The thin layer of oxide always allows an inductive charge to pass between metal gate and silicon. Metal gate is here, the gate, the silicon is down here. So inductive charge here, meaning creating a channel. Okay, kita induce. The channel is not there, but you want to induce. Okay, creating channel. Remember we talked about enhancement mode last time? Enhancement mode, MOSFET, for example. So if you talk about N-type enhancement, then it's going to be source drain of N-type, channel N-type, and you have to apply positive VG on the gate in order to start inducing formation of channel under the gate ox, right? So that's what it means by inductive charge, to pass between the gate and the silicon, right? The in between, the space in between is the channel under the gate ox, right? You can also use that as a dielectric material, of course, insulating material between metal layers, field ox in this case. Okay. Tunneling material, tunneling oxide allows electron to pass through oxide without resistance, a very thin oxide that can allow tunneling mechanism to take place. So let's have a look at the range, right? Range of thickness of the oxide for different functions. Okay, for example, you can see the thickness is on the y-axis, oxide thickness, and x to just category ya, kenapa? So we're stacking different rows of oxide. In this case, if you're talking about chemical oxide from cleaning and native oxide, so kita discuss native oxide now is in the region of 1 to 5, 1 to 3 nanometer. Okay, this is about 3 to 5, so it's within that region. Native oxide, if you just leave your silicon wafers on the bench exposed for a couple of hours or a couple of days, so this you're gonna get with native oxide on the surface. If you're talking about gate ox or tunneling oxide, then we're talking about oxide thickness below 10 nanometer. Okay, and you have to look into the different technology nodes, right, to get the correct number or the correct thickness of oxide. So if you go with thinner technology node, then you have to work with thinner oxide as well, right? But the typical range is below 10 nanometer. If you're talking about pet ox, so pet ox ni kita akan tengok nanti pet ox ni apa benda sebenarnya dalam fabrication steps. So pet ox is usually a couple of tens of nanometers, right? Tens of nanometers, pet oxide, and then masking oxide depending on the dopant type, temperature, diffusion time. So it ranges across. For example, now we talk about 0.03 micron. If talking about field ox, then it's one of the thickest one. Okay, 1 micron in this case, very, very thick. Okay, so this is thermally grown oxide. Yang mana kita guna silicon as the precursor for the oxide to grow. Okay, you consume the silicon. So the second category we talked earlier on, deposited oxide. Okay, you can deposit oxide using CVD, sputtering, some other processes that you're going to learn along this course. Kita akan belajar nanti. You can have masking oxide as well. You can also have other oxide for different roles that you can also introduce on the wafers by different processes, not only thermally grown oxide. So ada different quality ya, under thermally grown and deposited oxide. Okay. So a few summaries to show the evolution, if you like, in terms of the oxide properties. Okay, take out from 97 until 2012 at least, and it's already like 10 years ago. So minimum feature size back in the 90s was like 250 nanometer. Okay, So when I joined Silterra, Silterra still had, I think, 300 plus nanometer, and down to about 100 180, I think 180 nanometer, early 2000. So but they're based on the capability of the fab. Is the fab was already capable at that particular time, then of course they can manufacture a lot lower technology nodes. Tapi waktu tu kita punya capability was only down to 180 nanometer. And then before I resigned back in 2009, I think, 1 year before, I got to install a new equipment called ARF for lithography, argon fluoride 193 illumination wavelength that's capable of printing down to around 100 nanometer minimum. So this is the minimum capability that we have in Silterra for now. Okay, so if you look at the gate oxide, for example, then if you look at the evolution, it was 4 nanometer back in the 90s, down to around 1-2 nanometer. Okay, so field strength, maximum field strength that it can endure is, it has to be 5 megavolt per cm that you feel. Analog side, you can look at other parameters as well. So if you look at this roadmap, you can find this on ITRS. Now kita panggil dia ITRS, International Technology Roadmap for Semiconductor. Now tengok in the next few years, where are we going? What sort of technology are we talking about? What sort of applications are we discussing now? And it's going to be big in the future. Especially now we're talking about AI, 5G chips and all this stuff, right? Yang belum ada discussion back then. Okay. So this is how it looks like. One of the old furnaces. You can have a look at the recent one in the YouTube yang saya letak on Elon tu. Okay. So this is a stacked furnace. Dia ada 3 quartz eh. So this is going to be the quartz tube, quartz tube, quartz tube. So it's vertically, horizontally laid. Okay. So on the other hand, on the right hand side is the vertical tube. You're gonna see the tube inside vertical, so you can, so wafers will be something like that. Then they can vertically arrange. Tapi yang kiri punya horizontally, horizontal punya tube, tapi wafers are vertically arranged. Kalau tube vertical, wafers will be horizontally arranged, right? So summary of a simple oxidation process. Kalau you are in the lab, usually lab scale, you normally use this as your supply of the water vapor. You heat up, you do some vibration as well. You introduce vibration to improve the oxidation. Okay, then the water vapor will be supplied into the quartz tube. So you have your wafers here vertically arranged. And then there you go, you have the oxidation process, wet ox. On the other hand, if you run dry ox, then you're going to have oxygen coming in, oxygen gas coming in, wafers are vertically arranged in the quartz boat. Okay, and then you're going to have like exhaust line at the end for the byproduct of the process. Okay, there you have your dry ox process. Right, so as I said is now, when you run, when you perform silicon dioxide by thermal oxidation, you are going to consume some parts of the silicon. Okay, so some part of the silicon. So you start off in this particular process, you started off with this thick of silicon. You start off this silicon thickness in the original before you start the oxidation process. Then you're going to grow, say, 100 nanometer of oxide. Contoh, so you want to grow this, right? So during the growth process, some parts of the silicon will be consumed. Okay, some part of the silicon will be consumed. So that means to be able to get more and more oxide, you need to use more and more silicon on the surface. Okay, so your final thickness as you grow, okay, as you grow, you're gonna get oxide like that, and you're gonna consume, say, katalah ni ya, then nak grow this much, then you're gonna consume that much of silicon. And if you increase your silicon dioxide thickness like that, then you're gonna consume more silicon. Eventually sampailah we reach 100 nanometer, say this is the whole 100 nanometer, yang brown region, then you are going to consume this much of original silicon to be able to grow this much of oxide, right? So the rule that we use here, or the mechanism that's involved, is called 55-45. Okay, 55-45. So that means 45% of the silicon will be consumed. Okay, so yang ni you dapat the whole ni, tapi you akan consume silicon thickness on the surface, right? To be able to grow the oxide. If you want to see why is it 55-45, we have one calculation in the book, but this one shows 44-56. So dia ada plus minus. Dalam textbook ada yang cakap 56-44 instead of 55-45. And there is a calculation for that. You can have a look at Gary punya book kalau ada, ataupun I think online ada. You can find this PDF. Tak nampak lah. This PDF Gary punya book lah. Sebab saya pakai kamera susah sikit nak tunjuk. Ni buku ni. Gary punya buku ni. If you have this, or you can check online, you can go to page 43. 43, then you can dapat calculation, yeah. It's related to the molecular weight of the silicon, density of silicon, molecular weight of silicon dioxide. Then you're going to do some ratio calculation, and then you're going to end up with thickness of silicon on over thickness of silicon dioxide is 44 or 0.44. So check on page 44. Gary 44. Saya tulis kat sini ya, Gary 44. Untuk derivation lah, ya. Gary page 44. Is it 44? No, sorry, 43. Confused dengan ratio tadi. Gary 43 ya. Tengok macam mana boleh dapat 44%. And there's always a plus minus 1. Ada yang you'll probably find 55-45 or 56-44. Okay. So in essence, you are going to consume some part of the silicon in order to grow your silicon dioxide. Right, next, we're going to look at the kinetics of silicon dioxide growth. So what is actually happening during the growth process, okay? So there are mainly 3 steps that's going to be involved in the growth process. So the first one is oxidant. So either it's water vapor or dry oxygen reacts with the silicon atoms on the surface, okay, from the silicon wafers, of course. So the oxidant can be dry or can be wet silicon atoms from the wafers. Okay, so that's the very first step. We're going to look into that by the schematic down there. So step number 2 is silicon atoms are then consumed. Remember the previous page, 55-45 or 56-44 thing. So this much of silicon is going to be consumed in order to grow whatever thickness of your silicon dioxide. And then step number 3 is layer of oxide forms on the silicon surface. So the final silicon dioxide is formed as the result of the growth. Okay. So this can also be represented by this schematic down here. So you have your oxidant flowing, can either be dry ox or wet ox, okay? Dry ox or wet ox. And then you're going to have gas diffusion, water vapor diffusion, or dry oxygen diffusion on the surface of the silicon. So this is the silicon substrate. So this is the oxide that you want to form eventually, which will be made of silicon partly. Remember the rules now? So original silicon is semua ni lah. Tapi since some are consumed, so you're gonna see that, right? And then you're gonna have solid state diffusion, where your oxidants are diffusing into the silicon to initiate the growth process, and then eventually the silicon dioxide formation. Okay, so those are three main steps. Let's have a look at the details of these three steps. So linear parabolic model, the growth mechanism. So the first part is chemical reaction between silicon atom and oxidants at the wafer surface. So you have oxidants coming in. So remember O2 or H2O vapor, right? So you're gonna have chemical reaction between silicon and oxidants. And then reaction is limited by number of silicon atoms available to react with the oxidant. So remember, number of silicon atoms available. Okay, silicon atoms available maksudnya yang on the surface lah. Kalau banyak silicon yang available, then the more, the thicker the oxide that can be formed. So we'll see later on that you will get different growth rates for 100 silicon in comparison to 111 silicon. So let's make a guess now. If you're about to grow oxide, an oxide layer on silicon 100 versus silicon 111 at the same temperature for the same time, which wafer is going to give you higher oxide thickness? Is it 100 or 111? Relating to this point, are you going to get thicker silicon dioxide on silicon 100 or 111? Anyone? Any guess? See the points there? Reaction is limited by number of silicon atoms available to react with the oxidant. So 100 ke 101 yang lebih banyak silicon atoms available? Yang mana yang denser? Anyone? Any guess? Zik 100, okay. Others? Can write it down. Ifah Farzana, what do you think? 100 or 101? Yang mana yang denser? As we learned in 386. Remember last time we talked about 100 versus 101 when we discussed about carrier mobility, carrier transport, the mu E, mu H, and so which one is denser? IFA 100, okay. Others? How about Kali? Amiro 101. Kali, what do you think? 100 or 101? Alia 111, okay. Others? Sari Iziani? So we have two 3 111s, 2 111, 2 100s. Any other? 4 111. Okay. So the answer is 111, right? 111 is denser. So that's why the carrier mobility, electron mobility is lower in 111 in comparison to 100 because 111 is a lot denser. Therefore, below you dense, then carrier transport will be impeded somehow, right? So the mu is then lower. So you bawa aja the very same concept, the denser concept of 111 into this availability of silicon atoms for oxidation process. So the more silicon atoms available, the higher the growth rate, because the reaction at this point is limited by number of available silicon atoms. So that means you're going to get 111 to be higher in the growth rate, therefore the final thickness, compared to 100, okay? Higher. So ada banyak lagi silicon atom available on the surface, right? So that's why I always say that 386, in fact 307 solid state is related to 386 and related to 487. You cannot always go back to the previous fundamentals in order to understand the process. Process ni bukan completely independent of the fundamental physics. It's always related to it's always related to the fundamentals. Okay. So in fact, one of the strong points of our candidates, you our candidates, physics student, for fab punya position. Fab position is in the physics that you learn in comparison to engineering graduates, right? So don't be inferior if you are a physics graduate. So you learn more physics, right? Engineering kita belajar all this silicon atoms density, you know, the mu e, kenapa mu e in 1,1 is lower than in 1,0. So this is your privilege. So that's why if you talk about position like device technologies or fab integration engineer, technology development, dekat fab, usually dia akan prefer physics graduate because you have the background. In fact, baru ni pun Infineon, saya punya kawan dekat FA Reliability Department, minta saya recommend good physics punya graduate with strong semiconductor background in order to do the job in technology development, reliability. So this is your strength, right? So this is what you learn. So make sure you fully utilize whatever that you've learned before. It's going to be very, very significant in your career later on, especially if you're into these kind of applications, right? So it's related. During the first 500 nanometer or 50 nano, remember 1 nano is 10 angstrom. 50 pula, sorry. 1 nano is 10 angstrom. You can ingat, you have to ingat this forever. Kalau masuk fab, this is the unit that you're going to use a lot. Okay, 1 nano, 10 angstrom. The first 500 angstrom or 50 nano of oxide growth, the oxide grows linearly with time. Okay, during 0 to 50 nanometer or 0 to 500 angstrom, we tend to have linear growth with time. Okay, kan dapat macam ni macam tu with time, growth with time. Nanti kita akan tengok dia punya full model. So it's what we call it linear parabolic model. It starts off with linear, then parabolic model. Okay, get the reason. So growth rate begins to slow down as the oxide layer growth. So remember the reaction now at this point is limited by number of silicon atoms available on the surface to react with the oxidant, right? So bila you ada more and more oxygen sitting on the silicon, okay, bila you ada thicker and thicker silicon dioxide covering the silicon, does the oxidant get to see more silicon atoms available? More or less. Bila you dah ada oxide lebih tebal, over time tebal, oxidant coming in at the same time. Oxidant tu makin nampak silicon atom ke makin kurang nampak? You nak masuk contoh you nak dengar conversation bilik sebelah. Satu conversation dinding nipis. Kemudian tiba-tiba lama sikit dinding tu dah tebal. Can you listen to the conversation clearly, clearer or less clearer over time? Mula dinding nipis, mana dinding tebal. You are the oxidant. Dinding tu is the thermal oxide form and bilik sebelah tu is the silica lah. Less, right? Sebab dinding makin tebal, tak dengar kena lebih susah. So now at this point, after 500 angstrom, the oxidants get to see less and less silicon atoms because dekat tengah tu ada barrier, silicon dioxide, more and more silicon dioxide acting as the barrier. So dia dah tak dapat access the silicon atoms as easier as the start of the process, right? So that's why it will slow down the oxidation as the thickness grows thicker. Okay, so that makes sense, right? Senang je kan konsepnya. Konsep you dengar dinding tebal, macam tu je nak faham. Then we start to enter the parabolic stage. Remember linear, then parabolic model of the growth, right? In the parabolic stage, it typically begins when the thickness of the silicon dioxide hits about 1,000 angstrom or so, 100 nanometer, has been grown on the silicon. So as you have more and more oxide, this is your silicon now. Just to exaggerate, don't believe the scale. Just to exaggerate the scale of your oxide. Maksudnya silicon tu lagi thin, don't forget about the scale. Tunjuk thickness oxide. It's now thicker, say 1,000 angstrom or 100 nanometer. So the silicon atoms are no longer exposed directly to the oxidant. Macam nak dengar bilik tadi lah, dinding sekarang dah tebal, tadi dinding nipis. So oxidant are still coming in, but then this is now the barrier, the physical barrier. Silicon atoms semua duduk kat bawah ni, right? On the surface, still on the surface of the silicon wafer, but then the surface is now further down, okay? Further down. Instead of yang tadi dekat je, ataupun mula-mula proses memang silicon memang available directly to the oxidant, right? So to be able to continue the process, now the oxidants need to diffuse through the oxide. Dia kena lalu oxide ni, dia kena diffuse through the oxide in order to see, in order to reach the silicon. Okay, nak dapat, nak sampai ke, nak jumpa silicon bawah ni, in order to form thicker and thicker oxide, oxidants need to diffuse through oxide first. Jadi kerja dia lagi susah lah. Dia lagi susah untuk form more and more silicon dioxide. At this point, at this stage, the reaction is limited by the rate of diffusion. Okay. Remember the first one is now the linear part. The reaction is limited by the silicon atoms available on the surface because they are there already on the surface, right? We're waiting to do the reaction. On the other hand, in this parabolic stage, sebab the oxidants need to diffuse through the oxide first to be able to form or continue the process, the growth process. Now the reaction is limited by the oxidants diffusion rate through the oxide. Okay, that's why kita ada the linear and parabolic part. Okay, the linear part is the easier part. If you talk about the oxide thickness, Tox over time, let's say, then you're going to have this region where it's a lot easier and reaction is limited by the available silicon atoms on the surface as region 1, linear, okay, linear with time, and over time it's going to be a bit parabolic, it's going to be a bit slowed down due to reaction is now limited by the diffusivity of the oxidant through the oxide, okay, so they can slow down, and this linear parabolic is called Dilgrove model. It's described clearly by Dilgrove model. Nama dua orang, Dilgrove model. Mathematically describe the growth of an oxide layer on the surface of a material. Okay. In particular, it's used to predict and interpret a thermal oxide of silicon in semiconductor device fabrication. So model ni kita guna untuk predict and interpret. Okay. You can use the calculation later on the equation, plug in certain coefficients, certain parameters, certain details, and then you can predict what sort of thickness are you going to get after linear mode, after parabolic mode, right? The model was first published in 1965. See, this year is close to the Mohd law. It's Mohd law year juga. Modern mode, the observation, remember? 65 by Bruce, Deal, and Andrew Grove of Fairchild Semiconductor. Okay, so this is observed by and modeled by these two guys in Fairchild. Let me just see, just go through one more page, I think, before I stop. So what you see in this model, before we go through the equations in the next class, right, so this is your silicon. You just tadi kita discuss on silicon dioxide on silicon, so silicon dioxide on silicon. So to understand this illustration, just flip this 90 degrees anti-clockwise. Your silicon flip itu, so your oxide is going to be here on the left hand side, and then your silicon is going to be on the further right, and yang awal-awal is oxidant coming into the surface, right? So kalau you flip this, then you're going to get silicon all down here. Okay, silicon start kat sini sampai ujung silicon. Then you're going to get your silicon dioxide on silicon. So this is what you want to grow over time. And this is the gas flux coming in, the flux from the oxidant. So either it's O2 or H2O vapor, right? So F1 region, the first region is the region of gas transport flux. And this F2, this one is F1. F2 is the diffusion of flux through silicon dioxide. It's going to change over time because when you start the process, there's no silicon dioxide grown on the surface yet, but over time, as you cross close to 1000 angstrom, it's going to get more and more difficult because thicker and thicker oxides already formed. And F3 is a reaction flux at the interface of the silicon. So all the silicon atoms are available here for the reaction. Okay. So mula-mula you tak ada ni lagi, then your F1 is just directly on the surface, right? But there's no oxide in between. But over time, you're going to get more and more oxide. So you're going to see more and more diffusion of flux through the silicon dioxide in order to continue the reaction. Okay. So I'm just going to stop here first, and we're going to discuss in the next class mathematically what is F1, what is F2, and what is F3, and what are the constraints for each flux at each interface. Okay, so is it clear so far? 11:50. Is it clear as far as the process of oxidation is concerned? Consumption of silicon, kinetics. All good? Any question? Ada yang tak faham? Ada soalan? Before we go to the math next week. Tak ada? So tak ada soalan, assume semua orang faham Okay then, if there's no question, then yep, that's it for today's class. Almost 2 hours. So yeah, I'll see you next week, inshallah. Bye-bye. Take care. Assalamualaikum.